Okay, so welcome to the next talk today. We have Javier Rubio from University Madrid, Spain, and he's going to talk about Hubble-induced phase transitions in the Standard Model and beyond.
Okay, so thank you very much for the invitation. So I will benefit a lot from the things that Sanos was already introducing regarding the evolution of the universe. So in particular, the main focus of this talk is going to be related to what happens at the end of inflation. As he was saying, well, inflation is nowadays a kind of well-established paradigm, no? Able to explain the generation of curvature perturbations and then give rise to this glow that we observe in the CMB and to such a formation later on. And also, who knows, maybe at a smaller scale also to these primordial black holes that he was mentioning about. Okay, even though inflation is well established, we know very little about the inflaton itself. We don't know which is the nature of the inflaton. And therefore, we know also very little about which are the couplings of this inflaton to the standard model particles. There are direct couplings or indirect couplings to them. We don't even know which is the energy scale at which the onset of Big Bang or the usual Hubble Big Bang picture is starting. And we don't know either which is the equation of the state that is taking place after inflation. So we go right away to something like radiation domination, or there is something intermediate like matter domination, kination domination, or things like that. Okay. What I'm going to try to advocate here in this talk is that, there is already a very good tracker of the cosmological history in the Standard Model. That is the Standard Model Higgs. Okay, as any other scalar field, this field can be displaced from the minimum during inflation, so it can track the energy scale of inflation. And also afterwards, okay, it can be displaced by productions of particles during the reheating epoch. Okay. This situation becomes even more dramatic in the presence of non-minimal couplings to gravity, like the one you see in the lower part of the slide. Okay, this kind of coupling is indeed not a choice. Okay, it's something that is required for renormalizing the theory in QL space-time. So even if you set this non-minimal coupling to 0 as a given energy scale, it should be generated at a different energy scale. Okay, so in some sense, in the presence of this coupling, the Higgs field is able to track the cosmic history, and in particular the transitions between different cosmological epochs in which the rich scalar changes behavior. Okay, so it's sensitive to the cosmological history. Well, the model I'm going to present here is a rather simple scenario for starting the hot Big Bang after inflation. So the ingredients are minimal. So I'm going to consider the existence of a single field that is going to play a double role. It's going to play the role of the inflaton and also the dark energy field. So I'm having in mind in scenarios like quintessential inflation. I'm going to consider this non-minimal coupling of the Higgs field to gravity I was mentioning before, and that's all. So no additional degrees of freedom between the electroweak scale and the Planck scale. So the Lagrangian is something that you can write in a line. It's just the Lagrangian of the Standard Model, plus including the Higgs potential and the non-minimal coupling to gravity, plus an additional sector for the inflaton field. Okay. So in spite of the simplicity, the model has some interesting outputs. Okay. First, this non-minimal coupling is going to stabilize the Higgs field during inflation. So it's going to avoid that it's going to make that it cannot fluctuate during inflation. Therefore, it's going to avoid the generation of the subcurvature perturbations. And as we will see, we will find an appealing connection between the Standard Model parameters that we measure at low energies and the physics after inflation. Okay. And one of these interesting outputs is also the fact that the Higgs field itself can be responsible for heating the universe after inflation. Okay. Well, the main scenarios I was mentioning that I had in mind is this kind of quintessential inflation scenario. In this scenario, there are two periods of accelerated expansion, one in the early universe, inflation, that is associated to this first plateau that you see in the figure, and one period of dark energy domination nowadays that is associated to the second plateau in the figure. Okay, in the middle, since there is the potential does not have a minimum, okay, eventually once the slow roll condition is violated, the inflaton field is going to enter a period of kination in which its evolution is going to be dominated by the kinetic counterpart. Okay. Now, even although everything I'm going to say in this talk is formulated with this framework of quintessential inflation, the most important part for realizing the scenario we have in mind is this period of kination and not quintessential inflation. So if you're able to come out with any model like rotating action or things like that is able to give rise to a period of kination, still this kind of a scenario could be implemented in that model. Okay. So that's essentially the main ingredient. Well, these scenarios, as compared to other scenarios of inflation, is quite appealing because you don't need to completely destroy the inflaton condensate in order to reheat the universe. And the reason is that this energy density of the inflaton during this period of inclination is decreasing very rapidly, like 8 to the minus 6. So therefore, if you are able to produce a very small amount of radiation by any kind of mechanism at the end of inflation, since this radiation will scale slower than 8 to the minus 6, particularly 8 to the minus 4, you are guaranteed that you are going to enter into radiation domination at some point, even if you have not destroyed the inflaton condensate. Okay, this is completely different from the thing that happens typically in oscillatory models of inflation, where you have to be sure that you destroy the inflaton condensate. So the purpose of this talk is going to be generating this initial amount of radiation that later on will become to dominate the universe. Okay, so the scenario that we had in mind, as I was saying, it involves this non-minimal coupling to gravity. So let's focus on the Higgs sector, and let's focus in particular. We are going to work from now on in the unitary gates. So you see little h from now on is because I'm working in that gates. So the idea is that this Higgs sector is not participating in inflation, so it's energetically subdominant, it's an spectator field. So the full behavior of the rich scalar is dictated by the inflaton field, or if you want, by the dominant energy component at every cosmological epoch. Okay, and we're also assuming that even this coupling is there, the contribution of the Higgs field to the effective Planck mass is negligible. So this scenario is completely different from usual Higgs inflation scenarios, where the field actually participate in inflations modifying the effective Planck mass. Now, you see that the behavior of the rich scalar depends on the equation of the state of the inflaton. So during inflation, this equation of the state is -1. So the rich scalar is positive, and that makes that the Higgs field has an effective mass that is extremely large. It's super Hubble. Okay, so that is going to block the Higgs field at the minimum of the potential, and it's going to avoid it moving, and therefore it's going to protect the model from the generation of such curvature perturbations. Okay, so for all practical purposes, this field is not doing anything during inflation. The situation changes completely when you finish inflation, because then we are going to enter in this period of kinetic domination. Okay, so the equation of the state during kinetic domination is equal to 1, and if that happens, the rich scalar becomes negative. Okay, so the effective mass of the Higgs field in this effective potential changes sign and develops a tachyonic instability. So there is a new minimum that is appearing at very large field values, and the Higgs field is going to try to roll from the original minimum at 0 to this new minimum appearing at large field values. Okay, while doing so, as you see in the second image, it's going to pass through a region in which its effective mass is negative. Okay, you want the second derivative of this potential, and that is going to produce induce a tachyonic instability that at the level of the perturbations is going to give rise to particle production. Okay, so what we're going to do now is focusing at the very beginning of this symmetry breaking. Around there, everything is quadratic. The theory is a free theory. Okay, and everything can be solved analytically. So what I'm doing in practice is neglecting this lambda h to the 4 term for the time being. Okay, I'm just going to focus on the free theory for the time being. Well, the free theory is something that you can, well, written in the proper variables, as you see in the slide, can be written in terms of an effective mass that depend on this variable set that essentially is a rescale time, or rescale conformal time, if you want. Okay, so you have a free theory that you can solve with a time-dependent mass. Okay, and you can look at which is the amplification of the fluctuations of this field, assuming initial quantum fluctuations. Okay. So it's important this because something I'm going to show later. Some people were studying this previously to us, assuming a homogeneous approximation, and this is going to be completely inaccurate for a reason that will become clear in a second. So it's very important that you don't use an homogeneous description, you use rather a quantum description of the field with vacuum initial fluctuations. Well, the reason is this one that you see here. So this is just the same equation I was showing before, but in Fourier space for the different Fourier modes. So in the left panel, you see the evolution of the modes. So as you see, there is a huge amplification of the amplitude of the modes for a small momenta. So this is an infrared effect. That is associated, this amplification is associated to this tachyonic instability I was mentioning before. Okay, the figure in the right-hand side shows a quantity that is associated essentially to the anti-commutator of the field and its conjugate momentum. Okay, so this part is the part that is typically associated to the classical dynamics, and as you see in the formula just below the figures, essentially you can split the whole information of the relations between the field and the momentum in two parts. One part is symmetric and one part is antisymmetric. The symmetric part is, as I was saying, is related to this quantity f, and the antisymmetric part is the usual non-commutation that you have when you are dealing with quantum fields. Okay, so as you see in the picture, this quantity f is also growing very rapidly. So in some sense, the anti-commutator of the field is exceeding significantly the commutator of the field. That is just this 1/4 that you see there. Okay, and this is a sign that you are entering a kind of semi-classical regime. Okay, essentially you can neglect vacuum fluctuations, and everything can be described like stochastic variables. So this is important for us because, as I was saying, I can only follow the dynamics of the model when I'm very close to the onset of the symmetry breaking. Afterwards, I will have to include the lambda h to the 4th term. So, and I will have non-linearities in the problem. I cannot solve the equations mode by mode. So I need to rely on non-analytical techniques. And in particular, I will rely on classical lattice simulations that are only accurate in this approximation in which the occupation numbers, or you want this function f, is large. Okay, so this is just a check that we can indeed move to classical lattice simulations. Okay, these are the result of what you're seeing in the left-hand side of these images is just the field fluctuations. So it's just a snapshot of the lattice in the middle of the lattice. As you see, after the symmetry breaking, there is a large enhancement of fluctuation, and afterwards, there is a kind of oscillatory patterns in this around the new minimums of the potential. Okay, so this is the main reason why I was mentioning before that assuming a homogeneous components description is completely inaccurate, because in these kind of scenarios, the amplification of modes below the effective mass of the field, or the tachyonic effective mass of the field, is as important as the one of the zero mode. Okay? Indeed, you can see this in this energy distribution. This is so the first enhancement that you see in the left-hand side of the figure is the exponential enhancement associated with the tachyonic amplification. As you see, not only the kinetic energy is growing up, also the gradient contribution is raising, and also the ones associated to the interactions between the Higgs field and gravity, that is this kind of bluish line that I'm denoting like with I, with the interaction term. Okay, the important part is that in the long run, all these interaction terms with gravity are going to disappear just because, well, the Hubble rate is decreasing with time. And eventually, as you see in the picture, the blue and the green line start approaching. And this is a signal that the system is entering into some kind of equipartition between the kinetic and gradient components. Okay. That is going to be important for us because that moment of equipartition is what is going to define for us the reheating or the moment of reheating of the universe. Okay, so what we were doing in order to study this is running a lot of 3+1 classical lattice simulations. So you don't have to do it yourself. Okay, so we were scanning the parameter space for different values of the cell coupling and the scale of inflation and numerical coupling to gravity, and classifying several important quantities like the moment in which, the end of this the energy density that you produce in this tachyonic amplification, or the fraction of energy into the different components. For instance, in this plot, you can see the fraction of energy into gradients for different values of the cell coupling. And as I was saying before, this is important because, I mean, we are considering here a potential that is h to the 4, so it's just the Higgs potential, it's a quartic. So in this particular case, that will correspond to n equal to 2 in this formula using the lower part. The equation of the state is 1/3. So you will be tempted to think that nothing is changing a lot, because essentially when you are in this regime of gradient domination, you also approach the equation of the state equal to 1/3. Okay, but this is just a coincidence in this particular scenario. If you will take any other potential, like for instance chi to the 6 or chi to the 8, okay, the equation of the state in homogeneous approximation will be different from 1/3. Okay, while if you solve the system properly, you always arrive to an equation of the state that is exactly the one of radiation, precisely because of this dominance of the gradients. Okay? So we were studying other quantities, like the moment in which the universe entered So this equipartition is achieved, and we enter radiation domination. And also we are computing with lattice simulations the energy density in radiation at that time, and deriving fitting formulas for all these quantities that can be used without the need of running further lattice simulations. So once you have this moment in which the universe enters radiation domination, you can associate a temperature to it, to this time. Okay. Now it's important to realize that this temperature, that usually is what people call the reheating temperature, okay, is just an indication of the scale in which, or the energy scale at which you enter radiation domination. Doesn't mean necessarily that the system is thermalized. Indeed, if you just consider a simple model without gauge bosons, just the pure Higgs, you finish with a spectrum like the one you have in the figure that is far from being a thermal spectrum. Okay, indeed, it's a cell-similar spectrum that is going to evolve from turbulence very slowly, and you're only going to achieve thermalization much later. Okay, so it can be that the actual reheating temperature is slightly smaller than this temperature that we are defining here. Okay. Now, the situation in the standard model is slightly more complicated because the self-coupling that I was using in the previous simulation was a constant. Okay, I was running or using the typical values that you find in the standard model, but I was disregarding something that is extremely important, that is the running. Okay, the running of the quartic in the standard model is quite peculiar. Okay, so nature has chosen values of the Higgs mass and the Todd mass that allow you to extend the standard model all the way up to the Planck scale, as you see in these green or red lines in the figure, but also for large values of the Todd mass, around 173, 174 GeV, it opens the possibility that this self-coupling becomes negative at a scale much lower than the scale of inflation or the scale of preheating in this scenario. Okay? So in particular, this scale can be as small as 10 to the 9 GeV for sufficiently large Todd masses. Okay, so and this is problematic because, well, first it has a simple solution because we don't know in precise which is the relation between the mass, the Todd mass that you extract from oscillator experiments, if you want the reconstructed Pythia mass or Monte Carlo mass, and the one that actually enters in these equations, that is the MS bar mass or the pole mass in this computation. So there's always a 2 GeV uncertainty in the mass of the top that you have to take into account. So a priori, one should be a bit agnostic about which is the actual situation. But let's imagine that we are in the situation with the Higgs coupling, the Higgs cell coupling becomes negative at the intermediate scale. So the picture that I was showing before will change in this way. So still we will have our Hubble-induced vacuum, that is the one that was generated by this tachyonic instability that I was mentioning until now. Then remember that we had this quartic potential that was stabilizing this Hubble-induced vacuum. But now the lambda is becoming negative at a given scale, okay? And therefore, the potential becomes, unbounded from below, okay? It develops a barrier and develops indeed a new vacuum. I say unbounded from below, but in reality, in the standard model, this vacuum happens, or we believe it happens at super Planckian field values. Now you see the risk. We had a mechanism that is able to reheat the universe, with a very large temperature, 10 to the 9 GeV or so. But at the same time, we had a risk that in this process of reheating the universe, we are crossing the barrier and finishing in the true vacuum of the system now at very super Planckian field values. That will be a disaster because essentially energy will have a kind of anti-de Sitter stage, and there will be a collapse of our universe. So we had to avoid that possibility. In order to, well, this is more or less the situation I was mentioning. So the green and blue lines, more or less, or the oscillatory patterns describe the situation we were having before. So we have some technical amplification and then some oscillations. But the red one, for instance, that is associated to higher scales of inflation, is the one in which you cross the barrier and you essentially go to the new minimum of the potential. So in order to see or to understand in which part of the parameter space we can have successful reheating while being safe from these true vacuum and super Planckian field values, we were performing a full parameter space scanning. So in particular, what we did is implementing three-loop randomization group running of the Higgs coupling in the lattice, in cosmolattice. We were completely agnostic about the torque quark mass values, so we were considering torque quark masses between 170 and 173. Also, we were considering a wide range for non-minimal couplings to gravity, so something between 1, okay, that is the minimum that you require to avoid iso-curvature perturbations, and a value of 700, that is the typical value that you use when considering Higgs inflation models. And also about the scale of inflation. The scale of inflation, you want the scale of kination or the scale at the end of inflation. That is, we were considering something between 10 to the 6 and 10 to the 15 GeV. Okay, and we were running a lot of simulations. These simulations are shorter, so we can run a few more. So we're running like order 1000 3+1 classical lattice simulations and checking for two things: the existence of the barrier and that the energy density that we produce in particles on Higgs excitations is not larger than the height of the barrier, separating the false from the true minima. And this is more or less the parameter space that you find. So it seems that the model is kind of, well, these are regions that are excluded in the left-hand side plot for different values of the scale of inflation. So of course, if the scale of inflation is very high, the probability of crossing the barrier is higher, and this can only happen for very small values of the torque quark mass, around 171.3 or so. But in general, okay, if you go to 10 to the 10, masses like 172 or so are completely variable. So, but overall, the important part is that somehow this kind of scenario or Hitler scenario favors lower masses for the torque quark mass. Well, this is a similar plot in which we show also the variable parameter space, displaying also which is the reheating temperature associated. So you see that there are two regions. The lower one is this kind of blue-green excluded region. It's simply a region in which we are not able, the mechanism is not efficient enough, and we are not able to reheat the universe before the epoch of Big Bang nucleosynthesis. And the kind of orange one on the top is the one that is excluded by these lattice simulations we were performing, by this possibility of crossing the barrier. Okay, but as you see, even in this, for a wide range of the parameter space, for sufficiently small masses of the torque quark, the temperature can be as high as 10 to the 8, 10 to the 9 GeV. Okay? So it's a highly efficient mechanism in this case. Now, one of the things that I was not mentioning till now, well, I was insisting on the fact that the gradients are going to be extremely large. So it's natural to expect that there is going to be a production of a significant production of gravitational waves, or if you want second order gravitational waves, that are going to be sourced by the anisotropic transverse Trellis bar of the energy momentum of this scalar field, in this particular case, the Higgs field. Okay, so there's using the expression here. The usual contribution to this anisotropic tensor is enhanced by the presence of the non-minimal coupling to gravity. Okay. So we're also checking the production of gravitational waves from cosmolattice. And well, the variable parameter space is summarized in these plots here as a function of the scale of inflation in the left-hand side one, and as a function of the torque mass in the one on the right. So there are several additional excluded regions, or in particular, as you see on the top, there is this CMB bound. Essentially, we are excluding the possibility of generating a large amount of gravitational waves that will contribute to, or will give an extra contribution to the radiation, and they are bound from the CMB on that. But the main point to keep from these images is that the amplitude of the gravitational wave that you produce can be rather large, at the level of 10 to the minus 10 or 10 to the minus 12. Okay? However, the frequency of these gravitational waves produced by this mechanism is of the order of the gigahertz. So that is going to make essentially these gravitational waves unobservable by current technologies. Okay. But we will be okay. But we will be able to, in the future, to develop something that able to test this gravitational wave on the gigahertz. This will be the spectrum that you should expect. So you see, the spectrum that I'm showing here of gravitational waves has three parts. The part that is generated by the mechanism I was discussing is the peak on the right-hand side, this Higgs-induced peak. Okay, this is the one that is coming from the lattice simulation. Then you had also another slope in the middle that is this kination enhanced perturbations. This is nothing else than the amplification of the modes that were entering the horizon during kination. So this is completely independent. This happens in any model of quintessential inflation, even if you don't have this kind of symmetry breaking mechanism. Okay, so this is also it's just an enhancement because you have this period of kination. And finally, the plateau that you see in the left-hand side is just the primordial power spectrum from different values of the scale of inflation. Okay. Well, we were also checking if there is a possibility of testing the impact of new physics on this. Of course, in the moment you introduce higher order operators, you allow you allow for a more efficient stabilization of you make the potential less sensitive to the to lambda becoming negative, and in principle you can allow for higher scales of kination. And it's more or less what is shown in this plot. There's also, since you are introducing this higher order operator, the rescattering of the modes is going to be more efficient, and that is typically tend to displace the spectrum of the scalar perturbations towards the ultraviolet, and that translates also into the spectrum of the gravitational waves that will be translate to higher frequencies even. Okay? Well, although I was discussing here just things related to the reheating of the universe using the standard model Higgs field, we were using this kind of mechanism for several phenomenological aspects, including baryodensities, production of cosmic strings, domain walls after inflations, and also production of dark matter. That is something I will discuss in a second. So, okay, somehow the mechanism is rather versatile. And it's not restricted to reheating the universe with the Higgs field. So in general, you should expect that these Hubble-induced phase transitions happen in any kind of models in which you have the spectator fields that are non-minimally coupled to curvature invariance. Doesn't need to be specifically the Ricci scalar. And this is indeed a very natural triggering mechanism for phase transitions, because essentially there will be particular combination of this curvature invariance that will change sign at the transition between different cosmological epochs. So you have a natural clock in order to start the symmetry break. Okay? Well, in all this, if you're interested in this kind of mechanism, it's very important that you remember that all these processes are something non-thermal, non-perturbative, so it's something that you should never treat in the homogeneous approximation. In particular, it should be impossible to describe the production of topological defects if you don't use classical simulation techniques. And you should expect in general always a production of gravitational wave signature in these kind of scenarios. Just to illustrate the fact that this is not restricted to non-minimal couples with the Ricci scalar, in general you can consider an effective field theory in which you have some spectator field chi that is coupled to curvature invariance. So in particular, I'm showing here the action to next to leading order. Okay, so you have the coupling to gravity to the Ricci scalar I was considering till now, and you have higher couplings to curvature invariance in the last piece. Okay. So in particular, the effective mass of this spectator field chi will depend on all these Wilson coefficients alpha, beta, and gamma, plus the non-minimal coupling, plus the effective equation of the state of the universe at every particular cosmological epoch. So as you see, the effective mass is in the lower part. So the first two pieces is something, well, in particular, the second piece is something that we already know, is the one associated with this non-minimal coupling to the Ricci scalar. And the last piece, in general, is expected to be as a leading contribution, okay? At least if you want to stay within the limits of the effective field theory. But it's important to keep in mind that it can become relevant at a specific cosmological epoch. In particular, during a period of kination, the first piece in this effective mass vanishes. So this h to the 4 piece becomes now the leading order term in the corrections. So you can use this kind of higher order couplings to generate something subdominant. Of course, the mechanism is not going to be as efficient as before, okay, because you have to pay a price of suppressing the higher order operators with the cutoff. But we were exploring this possibility also of, within the context of the previous model, to study the production of dark matter after inflation. So we had a period of kination in which we reheat the universe using the standard model Higgs. And the moment radiation domination starts, this nominal coupling to the Higgs field becomes zero, and the higher operators in the game start playing a role. So in particular, you can induce also a transition between a phase transition in this spectator sector, okay, at the onset of radiation domination. And this essentially what you see in this image is just an illustration of this symmetry breaking. Again, you recover the same patterns we were discussing before. This is exponential amplification followed by some oscillations. And you're able to produce dark matter candidates that can be rather heavy, as you see in this plot, 10 to the 11, 10 to the 12 GeV. Okay. So, this is more or less everything I wanted to say. So, the main key point I would like you to remember is that, okay, in principle, couplings of a spectator field to curvature or curvature invariance are an efficient way of triggering phase transition beyond this having inducing stability. So the models are naturally equipped with a clock that is triggering stability at the onset at the transition between these cosmological epochs. Okay, we will consider specific models. In particular, we consider transition between inflation and kination in the context of the Higgs. But this is something that you can extend to other transitions among other cosmological epochs. But at least in the scenario I was discussing here, it provides a very efficient way of reheating the universe before big bang nucleosynthesis without invoking any direct coupling of the infraton to the standard model or to new matter sectors. Okay, so preheating takes place using the fact that kination is diluting the energy density infraton very rapidly and being able to produce a small amount of radiation that is eventually going to dominate the universe. Okay? So in all these kind of scenarios, they come together with some high-frequency gravitational wave signatures that, unfortunately for us, at least in the scenario we consider, they are always in the gigahertz regime, so not observable with current means. But again, I think that all this kind of setting is rather flexible and can be used for other purposes. Like, for instance, we were considering also this purely gravitational production of dark matter. Okay.